Yes, ma'am.
Yes, ma'am.
Now it is visible?
Yes, ma'am.
Yes, ma'am.
அவங்களுக்கு தெரியுதுங்கிறாங்க. புரியுது. Right? So do you want me to repeat these three mechanisms? Yes? Okay. So, in the substitution mechanism, this dopant atom occupies the vacant site. These vacant sites are already present in the silicon crystal due to point defects. So if the dopant atom occupies a vacant site, then it is called a substitution. Interstitial means the dopant atoms moving through the interstitial spaces or and occupying the interstitial spaces. That is, a dopant atom, if there are no vacant sites, they occupy the interstitial spaces. That is called as interstitial movement. The third type of movement is interstitial C. So actually, we are describing the mechanism through which the dopant atom move into the silicon crystal. So the next type of mechanism through which the dopant atom moves is this dopant atom. Sometimes, if it has lot amount of activation energy, what it does is it pushes the host atom away, creates a vacant site over here, and occupies this. This is called as interstitial C. So obviously, for interstitial C, this dopant atom need to possess a very high activation energy because it has to go through the interstitial space and push the host atom away, create a vacuum, and then it has to occupy the vacant site. Whereas
Okay.
for the movement through interstitial space, a dopant atom needs only a very small amount of energy. It has been calculated to be 0.6 to 1.2 electron volts, right? Whereas for a substitution atom, that is to find the vacant site and occupy the vacant site, a dopant atom needs 3 to 4 electron volts. So these are the three mechanisms by which a dopant atom goes and occupies the diffuses through the wafer. Okay. So for substitution,
Okay.
phosphorus, arsenic, antimony are examples. These are more prone to substitution mechanism. In interstitial dopants, examples for interstitial dopants, lithium, sodium, lithium, these dopants try to occupy the interstitial spaces. Interstitial C. For interstitial C, is copper, gold, nickel. These dopant atoms try to follow this mechanism. That is interstitial C. In interstitial C, it pushes the host atom away, creates a vacuum, and then occupies the vacant site. Okay. So we have seen what is diffusion, what are the three mechanisms through which the dopant atoms diffuse. Now, what are we going to discuss in this class? So in this class, we are going to look into the ways to determine how far the dopant atom or the impurity atom has gone into the wafer. And then we have to look at the change in doping concentration as we move from the surface of the wafer to the bulk of the wafer. That is from the surface to inside the wafer. So, point you have to calculate the junction depth. Now, I have to explain what is a junction. Junction means, let us assume that we are starting with a p-type substrate. That means the wafer is already doped with p-type impurity. Now, we are trying to dope that p-type wafer with n-type impurity, right? So we have a p-type substrate or p-type wafer. We are trying to dope n-type impurity into the p-type wafer. So actually the junction is formed where both the doping concentration, that is p-type and n-type impurity, becomes equal. So at the junction, this p-type impurity and n-type impurity become equal. That we call it as junction. Okay. So we have to find what is the junction depth and where is the junction formed. So at the junction, both the impurity, that is pre-deposited impurity and the impurity we are currently depositing should be okay. Then we have to find out the surface concentration. The concentration of the impurity in the surface of the wafer. Finally, after getting all the answers for this above question, we can arrive at the so the change in concentration from the surface to the inside of the wafer. So to find out this, we have to make use of Fick's law. So we are going to discuss one-dimensional mathematical analysis of diffusion using Fick's law. That's Fick's law says. The Fick's first law describes diffusion as J equal to minus D into dou N by dou X. So what is J? J is flux. What is flux? Flux is the number of molecules or number of atoms that crosses unit area per unit time. That is actually that rate of transfer of dopants per unit area is the number of atoms move across a unit area per unit time is flux. Okay. So what is D? D is diffusivity. What is N? N is the concentration of the dopant. What is X? X is the direction of the movement of the dopant atoms. So dou N by dou X will give you the concentration gradient. You might have noticed negative sign. So what does this negative sign indicates is this movement of dopant atoms takes place from a region of higher concentration to lower concentration. So this movement of impurity atoms is from a region of higher concentration to lower concentration. So that is signified by this negative sign. Okay. So D is the diffusion constant. So D is given by D equal to D naught e to the power of minus EA by KT, where EA is the activation energy. This activation energy was the energy required by a dopant atom to move through the or diffuse through the wafer. Okay, so and we can easily from this expression you can easily see that the as the temperature T is the temperature, EA is the activation energy, K is the Boltzmann's constant. Okay. So the diffusivity D increases with increasing temperature. D naught into e to the power of minus EA by KT. So when the temperature increases, the diffusivity also increases. Obviously, because if we increase the temperature, the carriers will get more energy to diffuse. So when the temperature increases, the diffusivity also increases. This is the first law. Now come to the second law. So second law is given by A into dou N by dou dx equal to minus A into J of x plus dx minus J of x. To understand this expression, please look at this diagram. So consider this parallelepiped. This dopant atoms, that is the impurity atoms we are trying to diffuse, moves from left to right. Assume that the dopant atoms are moving from left to right. Consider two planes, P1 and P2. Between these two planes, P1 and P2, there is a small incremental distance, dx. Now, see when the dopant atoms try to move to P2 from P1, in this area dx, there might be some vacant sites. So if it finds a vacant sites, what these dopant atoms do is, they go and occupy the vacant sites. So the concentration of dopant atoms, when you compare the concentration of atoms in the plane P1 with the concentration of dopant atoms in P2, obviously the concentration of dopant atoms in P2 will be less. Yeah? Can you all hear me?
Ma'am?
Can you all hear me? Actually, my
Yes,
my
ma'am.
Yes,
connection.
ma'am.
Yes, yes.
Yes,
Yes,
ma'am. Yes,
ma'am.
ma'am.
Disconnectivity in my network was, so I thought you might not be able to hear me. Okay, so
Okay,
this
ma'am.
left hand side, dou n by dou t into A dx refers to the rate of accumulation of dopant atoms between the planes P1 and P2. Okay, so this represents the change in concentration of the dopant atoms. This change in concentration happens because some of the dopant atoms while crossing from P1 to P2 occupies the vacant sites in this area, that is dx. Okay. Now consider only the right hand side. See, here they have written as j of x minus j of x plus dx. So look at it from another angle. What is flux? Flux is the movement of atoms per unit area per unit time. So here some atoms may be trapped, dopant atoms may be trapped over here. So there is also a decrease in flux because some atoms are trapped here. So this area A into j of x minus j of x plus dx. So will be actually equal to this change in concentration. So he has formulated a equation like this. So the both means the same. So the left hand side means the change in concentration of the dopant atoms. Here right hand side means the change in flux of the dopant atoms, which are same. We are looking at the problem from two different angles. This is change in flux, whereas this left hand side signifies the change in concentration. Concentration or change in flux happens due to the occupation of the vacant sites by the dopant atoms in this place, dx. Okay. So we are rewriting the equation. Dou n by dou t equal to minus j into x plus dx minus j of x by dx. Okay. So dou n by dou t equal to minus dou j by dou x. So how did we arrive at this? So you see, RHS was minus j into x plus dx minus j of x by dx. So actually, if you put the limit, that is let us assume that the small incremental distance dx, when dx tends to 0, then this expression j of x plus dx minus j of x by dx becomes dou j by dou x. So we repeat this minus j of x plus dx plus j of x by dx equal to dou minus dou j by dou x. Okay. So we have simplified the fifth second law as n by dou t minus dou j by dou x. Use first law, you substitute for j. J is given as j equal to, this is the first law, j equal to minus d into dou n by dou x. So you use this fixed first law here, or you substitute this for j over here. That is for this j, you substitute minus d into dou n by dou x. So you substitute, this negative sign goes away. So dou n by dou t equal to dou by dou x into d into dou n by dou x. We have substituted J from Fick's first law. Now our question is, so we have used two laws. We have substituted the Fick's first law in the second law and we have arrived at an expression here. Now we have to decide whether D, that is diffusivity, is constant or variable. So let us first assume that D is a constant. Let us assume that D is a constant. So now since D is a constant, we can take it outside. So I have taken D outside and have written as dou squared n by dou x squared. So dou n by dou t, that is the rate of change in concentration of the dopant atoms, is equal to d into dou squared n by dou x squared. This is called as Fick's simple law of diffusion. This is called as Fick's simple law of diffusion because we have assumed the diffusivity to be constant. Actually, practically, this is not the case because diffusivity increases with temperature. Because we actually increase the temperature, the dopant atoms have more energy, so they can diffuse into the wafer. And also, if we increase the time also, the diffusivity increases. But for simplicity's sake, we are first assuming this diffusivity or the D to be constant. So according to this above assumption, we are going to calculate the doping profile. So for that, let us take the case of infinite source. What do you mean by infinite source? So I said while diffusing, we have to heat the wafer in the ambient of, in the dopant ambient, right? So here we say the dopant source is infinite. What do you mean by infinite source? See, if you dissolve salt in a water, if you if you add small amount of salt, then the salt will dissolve in water. You go on adding more amount of salt, then what happens? When it is not able to accept the salt, then the salt will settle at the or precipitate at the bottom of the. So this means the water is not able to accept more amount of salt. That is, it has reached its solubility limit. So infinite source means that is the solubility limit has been reached. That is called infinite source. Infinite source means the silicon wafer can accept only to a certain amount of dopant. So that is fixed by the solubility limit of the silicon wafer. So if you supply a source above that limit, then we can call that source as infinite source. So the infinite source is fixed by the solid solubility limit of the wafer. So now let us fix the boundary conditions and find out the total amount of dopant in the wafer. That is the total concentration of dopant in the wafer. So N is concentration. So actually N of x comma t, right? So x represents the distance from the surface of the wafer to the bottom of the wafer. So x is the distance from the surface of the wafer to bottom of the wafer, and t is the time for which the diffusion takes place. So let us define the boundary conditions. When x is 0, right, then what would be the concentration of dopant? N0. Okay, let us take it as N0. At the surface, this is N0, right? So that is x equal to 0 means at the surface. So at the surface of the wafer, the concentration is N0. So when x is equal to infinity, that means at the bottom of the wafer. So at the bottom of the wafer, surely there will not be any dopant because we are only now starting the diffusion. So this is 0, right? So these two are the boundary conditions. X is equal to 0 and x is equal to infinity. X is equal to 0 means surface. Surface of the wafer. At the surface of the wafer, the concentration is some N0. At the bottom of the wafer, we have not started the diffusion yet. There is nothing there is no dopant in the bottom of the wafer, so it is 0. So these are the boundary conditions. What is the initial condition? Let time t be 0. So when we are starting the diffusion, there will not be any dopant atoms. The concentration of dopant atoms will be 0. So this is the initial condition. So now we are going to solve this equation, third equation, that is dou n by dou t equal to d into dou squared n by dou x square, by using this boundary and initial conditions. Okay. So when we solve this third equation using this boundary conditions, we get this equation: n of x comma t is equal to n naught into complementary error function. C represents the complementary. So complementary error function of x by 2 into root of dt, where d is the diffusivity, t is the time, x is the distance from the top of the wafer to the bottom of the wafer, and n0 is the initial concentration of the dopant. Okay, that is surface doping concentration. N0 is the surface doping concentration. Now look at the graph. So the x-axis represents the distance of the wafer from the surface to the bottom of the wafer, and this y-axis represents the concentration of the dopant atom. Okay, so see, you can see this N0. N0 is nothing but the surface doping concentration. At the surface, what is the concentration of the dopants? At the surface of the wafer, what is the concentration of the dopant? NB is the background doping concentration. Actually, it is the concentration of the dopant introduced before diffusion. That is, actually, I was while defining the junction, I told you that we are trying to diffuse an N-type impurity into P-type substrate. So this NB actually represents the doping concentration of the P-type wafer. So this is NB, right? Can you get the point? Yes?
Yes, ma'am.
Background concentration.
ma'am.
Actually, what we are trying to, a junction is formed only when there is both P-type and N-type impurity. So what we are
N-type.
trying to do is, we are starting with the P-type and we are trying to diffuse N-type impurity into it, right?
Okay,
So
ma'am.
a junction
Okay,
is
ma'am.
formed. Okay, so a junction is formed when this at the place where this P-type impurity and N-type impurity are same. So see, this NB represents the background concentration of the dopant, that is P-type impurity. In our case, P-type impurity. So this is the concentration of the P-type impurity, right? This is a second one. And this graph shows three curves. One taken for time t1, another t2, t3, and t3 is the highest value. So that is, this graph signifies diffusion has taken place for a longer time when compared to t2 or t1. So t1 is smaller, so t3 is highest, right? Now, if you see the graph, this this is this graph or this curve cuts this NB at this point. So at this point, the dopant, we have this N-type impurity and the impurity due to this P-type impurity are same. That is, NB represents the P-type impurity in our example, and this curve represents the N-type impurity. Both are same at this point. So here the junction takes place. So at this point, this point, a junction has formed. That is, from the surface, this is the, here x equal to 0, right? So this point is x equal to 0. X equal to 0 means surface of the wafer. So at this point, a junction has been formed when you diffuse for a time t1. Similarly, when you diffuse the wafer for a time t2, at this point, so this is the top of the wafer. At this point, it has traveled. This junction goes deeper. So if you increase the time, the junction goes deeper. Right? So can you get that point?
Yes, ma'am.
Yes.
Yes,
So
ma'am.
Yes, ma'am.
this represents the surface of the wafer. Okay. So this point where this NB line cuts this graph actually represents the junction, because the concentration due to N-type impurity and the concentration due to P-type impurity are same here. So at this point, a junction is formed. Okay. So when you increase the temperature, the junction goes deeper, right? So this and this what is this complementary error function? Complementary error function is nothing but 1 minus error function. Yeah, 1 minus error function. Okay. Now, this error function, this complementary error function is given by the formula 2 by root pi integral 0 to x e to the power of minus z squared into dz. So, there is no derivation for this. You just have to take it at x equal to 0. So, whenever I mean x equal to 0, then it means that we are talking about the surface of the wafer. So, at the surface of the wafer, that is at x equal to 0, n equal to n naught. So, surface concentration always constant in this infinite source diffusion and is given by the solid solubility limit n naught, because this is infinite source. Infinite source means you are having a dopants the amount of dopants is greater than the solid solubility limit. So the surface concentration always remains constant. Now, to obtain the total amount of impurity introduced into the wafer, we have to find out the area under this curve. Okay. So this shaded portion will give you the total amount of impurity introduced into the wafer. So by integrating this curve, you can find out the area. So let me represent the total amount of impurity introduced into the wafer by a letter Q. So Q equal to integral 0 to infinity n of x comma t into dx. Actually, I am trying to find out the total amount of impurity introduced into the wafer by integrating. We have to find out the area of this curve. So you integrate from 0 to infinity n of x comma t into dx. So now Q equal to, so I'm, yeah, actually this n of x comma t into dx, yeah, you have to replace this by n naught complementary error function x by 2 root of dt. So I'm replacing this n of x comma t by n naught complementary error function x by 2 root of dt. See? Q equal to integral 0 to infinity n naught error function complementary error function x by 2 root of dt into dx. Okay. Now I am changing this x and dx to dz and z. That is, you take this x by 2 root of dt to be z. Take x by x by 2 root of dt to be z. Okay. So if you differentiate the above dz, that is, you will get dx by 2 root of dt. So if you substitute this equation, you will get, that is, you for the x and dx, you change it to z and dz using this. So if you substitute and see, you will get this expression. The q equal to n naught 2 into root of dt integral 0 to infinity complementary error function z into dz. Okay. So this value, if you find it out, this value, that is complementary error function of z into dz value, this integral value will work out to 1 by root pi. So I'm substituting for this the value, that is q equal to n naught into 2 into root of dt into 1 by root pi, where q is the total the constant or the total impurity introduced into the waveform. So again, just rewriting the expression, q equal to 2 n naught into square root of dt by pi. Now, what is this dt? D is the diffusivity and t is the time. Actually, dt is called as diffusion length because the unit of d is centimeter squared by second. So d into t means centimeter square by second into second. Unit of d, the diffusivity. So actually they call this root of dt as the diffusion length. I'm explaining why this is called as diffusion length. Root of dt is called as root of dt. Root of dt is called the diffusion length. They are called as, it is called as diffusion length because when you look at the units, the unit of d, diffusivity, is centimeter squared by second. So dt equal to centimeter squared by second into second. So this seconds cancel away. So root of dt will give you centimeter. So root of dt has an unit of length. So it is called as root of dt is called as root of dt has unit of length and is called as diffusion length, or in other words, junction depth. So this dt gives you the depth of the junction depth. Okay. To find the junction depth,
Hello.
we need to know the
Prasanna. Okay.
doping
வருது
concentration.
ஓகே ஒன்றும் பிரச்சனை இல்லை.
To find
இப்ப 3
junction
கிளாஸ் போயிட்டு
depth,
இருக்கு. நான் சாருக்கு ஒரு 2 கிளாஸ் மெசேஜ் போட்டுட்டேன்,
to
ஐடியும்
find
பாஸ்வேர்ட்.
junction depth, we need to know substrate doping
நிவேதா
concentration.
பிசி ஒன்னு போயிட்டு இருக்கு சிவில்ல.
NB equal to concentration of dopant in the substrate before diffusion. Okay.
மேம் நீங்க பேசுறதே கிளியரா கேட்கலைங்க மேம்.
எம்பிஏல கொஞ்சம் கொடுத்துருக்காங்க, அவங்களும் பாஸ்வேர்டு கொடுக்கல.
Someone has entered this.
பாஸ்வேர்டு கொடுக்கல, அதனால பாஸ்வேர்டு இல்ல.
Yes, ma'am.
Okay. Let me repeat. So, do you want me to
ஆமா
root of dt?
என்ன கிளாஸ் என்ன 7:30 to 8:30 எல்லாம் போட்டு வச்சிருக்காங்க. நான் பாக்குறேன்.
Hello, can you hear me? Yes.
Ma'am.
Ma'am, someone.
Ma'am, cross talk, ma'am.
Ma'am. I don't think it's cross talk. Actually, it is from the college. I think they are checking.
Okay, ma'am. Okay, ma'am.
Okay.
Okay, ma'am.
Okay. So maybe I do not know how to mute it. In the next class, I will try to mute the other disturbance, right? Okay.
Okay.
ma'am.
Wait. So what is dt? So I was trying to explain. Root of dt is called as the diffusion length. Diffusion depth. Just wait for a few minutes.
அது வேணா ஒரு மெசேஜ் போட்டு ஷெட்யூல் பண்ணதுன்னா ஷெட்யூல் பண்ணது கிளிக் கேட்டுட்டு இந்த மாதிரி ஷெட்யூல் பண்ணிருந்தா ஷெட்யூல் பண்ணதை கிளிக் பண்ணி உள்ள போக சொல்லு. புதுசா ஒரு மீட்டிங் கிரியேட் பண்ணி
அவ்வளவுதானே. எதுனாச்சு? என்னடா வராது விடு. Can you hear me now?
Yes, ma'am.
Yes, yes.
Yes, ma'am. Yes,
Is it
ma'am.
clear now?
Yes, ma'am.
Yes,
Yes,
ma'am.
ma'am.
Okay, okay. So the unit of dt. Yeah. Is there any interruption in your video?
No, ma'am.
ma'am.
No, no interruption.
No,
No, ma'am.
Then we'll continue.
Your voice is not clear, ma'am.
Voice is not clear.
Yes, ma'am.
Okay. Okay. என்னாச்சு நான் வைக்கல நீ வச்சுக்கோ இப்படி வா so NB equal to, so NB is the concentration of dopants in the substrate before diffusion. That is, actually in our example it refers to the concentration of the p-type impurity. So we have started out with the p-type substrate and we are trying to diffuse n-type impurity into the p-type substrate. So this NB actually refers the p-type impurity, right? So this NB is given by NB equal to N0, where N0 is the surface concentration, complementary error function of Xj by 2 into root of dt. So this root of dt refers to the junction depth, or it refers to the junction depth, and xj also, actually this root of dt is called as diffusion length and xj is refers the junction depth. So solving for xj we can get the junction.
Ma'am, XF wang, ma'am. XJ wang, ma'am.
XJ.
xj j
Okay, ma'am.
right? So root of dt gives you
Okay,
the
ma'am.
diffusion length, whereas xj gives the junction depth. So when you solve for xj in this equation, you will get the junction depth. So if you look at this equation, this junction depth depends on NB, that is the concentration of the p-type impurity, and N0, that is the surface concentration, and also it depends on the diffusion length. So this depth, junction depth depends on, see we are concentrating more on junction depth because in manufacturing, that is in designing BJT, base depth, that is the emitter base junction depth and the collector base junction depth is very important. So we have to, the junction depth should be precisely controlled. So junction depth is a very important parameter. So we have to find out the junction depth. So we have to find out on which parameter this junction depth depends. So this junction depth depends on the NB and N0, the surface concentration, and also on dt, that is diffusivity and time. So diffusivity in turn depends upon the temperature. So if you increase the temperature also, the diffusivity increases, and it depends on the time. So if you diffuse the dopants for a longer time also, the diffusivity increases. So for deep junction, diffusion needed to be for longer duration, or you can increase the temperature by increasing diffusivity. Practically, we can control diffusion with either time or temperature. That is, if you diffuse for a longer time, then the diffusivity increases, or if you increase the temperature also, the diffusivity increases. So we have two parameters to play with. Okay.
Okay.
So actually I was actually diffusion takes place in two steps. One is pre-deposition and the second is drive-in step. One is the pre-deposition. So pre-deposition means actually we heat the wafers in the presence of a dopant ambient, right? So when you heat the wafers in a reactor in the presence of a dopant, then it is called as pre-deposition. After then what we do is in the next step, we remove the dopant, we remove the source of the dopant, and then we heat the wafers alone. That is, when the source of the dopant is shut off and the ambient temperature is increased, the impurities can enter the semiconductor. This is called as drive-in step. So actually we perform diffusion in two steps. In the first step, we heat the wafer in the presence of dopant. So dopant source. In the second step, we remove the dopant and then heat only the wafer alone. Now the dopants which have entered in the previous step, that is the pre-deposition step, goes deeper into the wafer in the drive-in step. So these are the actual two steps in which the diffusion is carried out. Okay, the total, so the impurity that has entered during the pre-deposition step is actually driven into the wafer. So the total amount of impurity is fixed by the pre-deposition step. So after the pre-deposition step, the source is shut off and the temperature is increased. So the impurity is further driven inside. This is called as drive-in step. So now let us find out what happens here. Okay. So the total amount, so we are trying to find out the concentration of impurity during the drive-in step, right? So the total here in the drive-in step, the total amount of impurity is fixed because in the pre-deposition step, we are heating the wafers in the presence of dopants. Whereas in the drive-in step, we are removing the dopants and heating the wafer alone. Heating the wafer alone. So the total amount of impurity is fixed by the pre-deposition step. We are now trying to calculate the total amount of impurity in the drive-in step. So the total amount of impurity is given by integrating n dx from 0 to infinity, which is given by q. So q gives the total amount of impurity. Now this n of infinity comma t. So see actually n of x comma t, right? So concentration, variation of concentration with respect to distance from the wafer surface and the time for which the diffusion takes place. Okay. So if x is infinity, that means it is at the bottom of the wafer where there will not be any dopant. So this is 0. So these two are taken as the boundary condition. So n of x comma 0, here t is 0. So t is 0. So we are starting the time equal to 0. So this is an initial condition. So using this boundary condition and initial condition, we have to integrate this equation to get the total amount of impurity. So after so if you draw the graph with n on the y-axis and x on the x-axis, then you get 3 curves depending on the time. Here time t3 is higher than that of t2 and t2 is higher than that of t1. Okay. And NB is the background concentration, which actually in our case signifies the concentration of p-type impurity. So when you compare these 3 curves, that is this curve, the variation in concentration of the dopant in the wafer for a longer time, whereas T1 is the variation in concentration of the dopant for a smaller time. And this these 3 points refers to the surface concentration. Look at the curve for T3. The surface concentration is very low, right? surface concentration is very low. Look at the curve for T2. T2 is smaller than that of T3. So if you diffuse for a smaller amount of time, then the surface concentration is higher. So consider this T1. T1 is very small amount of time when compared to T2 and 3. Surface concentration is higher. So when you diffuse for a longer amount of time, then the dopants at the surface move deeper into the wafer. That's what we can understand from this curve. So when you diffuse for a longer amount of time, the surface concentration comes down and see this is the point. This is the point where the junction is formed. Okay, so the junction is formed at a shallow distance. See, so this is a surface. So in the first case, that is the T1 case, the junction is formed here. See, the junction is formed here. Whereas for T2, the junction is formed here. For T3, the junction still goes into the wafer and forms here. So if you want the junction to be formed in depth into the wafer, then you have to diffuse for a longer amount of time. Okay, got it? Yes?
Yes, ma'am.
Yes, ma'am. Yes, okay.
Yes,
Is my voice audible?
Yes, ma'am. Audible, ma'am.
Okay, okay. Now let us solve this. On solving this differential equation, that is n of x comma t equal to q by root of pi into dt e to the power of minus x squared by 4 dt, we can get the doping profile. The doping profile obtained is a Gaussian profile. That is the surface concentration, that is the concentration at the surface where x equal to 0 is given by n of 0 comma t is equal to ns. Ns is nothing but it represents the surface concentration is given by q into root of pi into dt, because if you put x equal to 0 in this expression, e to the power of minus x squared by 4 dt, to find out the surface concentration, put x equal to 0. So this term becomes 1. So n of 0 comma t. So you put x equal to 0 in this expression. This term changes to 1. So the surface concentration ns, you get it as q by root of pi into dt. So with drive-in carried out for a longer time, surface concentration decreases and dopants move further into the semiconductor. Okay. So if you carry it out for a, that is, see, ns is inversely proportional to the time. So if you increase the time, then surface concentration comes down. That's what we see in this. That's what we saw in this graph. So if the diffusion is carried out for a longer time, then the surface concentration comes down. So T3 signifies that the diffusion is carried out for a longer time. For a longer time, the surface concentration comes down. That's what in the equation form we are seeing here. See, ns is inversely proportional to time t. So when the diffusion is carried out for a longer time, then the surface concentration comes down. That means the dopants on the surface of the wafer moves into the wafer, moves deeper into the wafer. Okay. So the junction depth at the junction, n equal to nb, we know. So when n equal to nb, we call it as junction. Okay. So ns is given by q by root of pi into dt, and nb is given by ns into e to the power of minus x squared by 4 dt. At x equal to xj, nb is given by ns into e to the power of minus xj squared by 4 dt. See, the above expression at xj, we are replacing this x by xj. So this xj represents the junction. Okay. Xj is proportional to root of dt, right? This junction depth is proportional to root of dt. We know that dou n by dou t equal to dou by dou x of d into dou n by dou x. That's a fixed law, right? So we have assumed that d is a constant. Is d a constant? We cannot be sure. It depends on the circumstances, right? So actually in the first place, simple diffusion case, we have assumed d to be constant. But let us now assume that d is proportional to n. So d is proportional to n, first case. So d is proportional to n means we can let us introduce some proportionality constant k. So d equal to k into n. So at the surface, if we consider the surface, this same equation can be rewritten as ds equal to k into ns. You find out k from this. So k equal to ds by ns. You substitute this k value in this equation. You substitute k equal to ds by ns in d equal to kn. So d equal to ds by ns into n. See, we have assumed d is proportional to n. See, we just assumed. We know that diffusivity increases with concentration. What if d is proportional to the square of the concentration? Then what happens? We do not know exactly whether d is proportional to n or d is proportional to n squared or d is proportional to n cube or d is proportional to square root of n. We are not able to find out. So what we do is we take three cases where d is proportional to n, d is proportional to n squared and d is proportional to n cube. So when d is proportional to n cube, n squared, then d is given by n squared by ns squared into ds. If d is proportional to n cube, then d is given by n cube by ns cubed into ds. So we have taken three cases in which we have assumed d is proportional to n or square of n or cube of n using computer simulation methods. Using computer simulation methods, we have arrived at a graph. We have arrived at a graph. This x-axis, we have plotted a normalization value, that is n by ns. We have normalized the concentration of the impurity atom. We have found out the ratio of n by ns and we have plotted it in the y-axis. In the x-axis, we have plotted the x. Okay. So we have taken these three cases. So this is, in this curve is nothing but, in this curve we have taken diffusivity to be proportional to n. In this curve we have taken d to be proportional to n squared. This curve we have taken d to be proportional to n cube. Now this is the surface concentration. So the surface constant, let us assume the norm, we have taken a normalized value. The normalized value is 1.0. So this is the surface concentration. So if d is proportional to n, then the change in concentration is like this, right? And it forms a junction depth at a point of 0.8 units from the surface. Suppose if d is proportional to n square, then the change in concentration follows this path and the junction is formed here, somewhere between 0.4 and 0.8 units from the surface. If suppose if d is proportional to n cube, then we get a curve, that is a change in concentration follows this path and a junction is formed at 0.4 units from the surface. So now think about this. Think about the three cases. One, D is proportional to N. Second, D is proportional to N square. D is proportional to N cube. If D is proportional to N, then you consider this. D is proportional to N squared. So for every square in increase of concentration, D increases. Whereas consider this, D is proportional to N. For every increase in concentration of impurity atoms, diffusivity increases. So D has more power in this case. That is, when the concentration increases, D also increases proportionality. Whereas only when the concentration increases in square, this increases. Suppose if it increases 2 times, this can increase only 1 time. So here D has more power if D is proportional to N. So when D is proportional to N, the diffusivity has more power. So more diffusion takes place, and so the atoms from the surface move very deep into the substrate and forms a junction. See, whereas this D cube, that is D is proportional to N cube, the diffusivity has less power. With more amount of concentration only, the diffusivity increases. So diffusivity is very less, and so a junction is formed at 0.4 units from the surface. 0 signifies the surface. Okay. 0 signifies the surface of the wafer. So junction becomes shallower for D proportional to N than D proportional to N cube. And also you can see this is the case where D is a constant. So for these 3 curves, we have assumed D is proportional to N, D is proportional to N squared, D is proportional to N cube. Whereas in this curve shows that D is a constant. So in this case, the variation in concentration is shown here. So these 3 curves, in these 3 curves, this curve, there's a sudden drop, right, for this curve. So there is a box-like profile. So this is called as due to the abrupt fall. So suddenly it falls from the surface concentration. These 3 curves try to follow this curve. That is, this curve signifies where that D is constant. Okay, these 3 curves shows the dependence of D on N squared and N cube. So comparing this curve where D depends on the cube of the concentration, there is a sudden fall from the surface concentration and it forms a shallower junction. So we get a box-like profile. Okay. So let us now express this pre-deposition step by a equation Q equal to 2 into N naught into root of D1 into T1 by root pi. In the drive-in step, Ns is equal to 2 into N naught by pi into root of D1 T1 and by D2 T2. So practically, usually, the drive-in temperature and drive-in time will be higher than that of the pre-deposition step. This D1 T1 represents the diffusion coefficient during the pre-deposition time, and the T1 signifies or represents the time of the pre-deposition, whereas T2 represents the drive-in step. In drive-in step, the diffusivity is also higher and the time is also higher and the temperature is also higher. So actually diffusion in VLSI circuits takes place in 2 steps, pre-deposition and drive-in step. Okay. Hello? Are you all online?
Yes, ma'am. Yes,
Yes,
ma'am.
ma'am. Yes, ma'am.
So today we have seen about the diffusion, right? So diffusion takes place in two steps. One is pre-deposition and driving step.
Okay.
Pre-deposition and driving step, and it takes place through three mechanisms. Diffusion takes place through three mechanisms. One is substitution, interstitial, and interstitial C. Right?
Okay. Okay.
Okay. So we try to find out
Ma'am, pay-per-view agling, ma'am.
paper view. நான் என்ன பண்றேன்னா I'll take photos of this all these notes and I will post it in your mails or in the group Vlsi group.
Okay.
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 So
Okay,
that
ma'am.
you can. This is a very important question, right? Fix first
Okay,
law and
ma'am.
second law. Okay. I'll
Okay,
send you
ma'am.
the notes. Okay.
Okay,
So
ma'am.
if you go through and please go through, and if you have any doubts, please ask during the Wednesday class. Wednesday
Okay,
morning we
ma'am.
are having class, no?
Yes, ma'am.
Right? Okay.
Yes,
Yes,
ma'am.
ma'am.
Yeah, I think I've completed the portions now. I'll take photos and now I will post it. Okay.
Okay.
Okay.